Everybody get a handout. Chapter 12. Okay, everybody uploaded their quizzes.
Well, it's up.
For next week, we got a lot to cover. What are you that face? What's that? Today's Wednesday. Have you guys all tangled up? You can't remember the date?
No.
You worked last night?
That's what we got earlier.
So to calculate the mass, it's the value of electricity, right? For the mass value of this.
We're finding the rules again.
Calculate the mass of water.
Divided by the weight of equals. No, it's like the geology.
Everything else comes later. So we're like.
Maybe it was that. No. The temperature. I'm sure it's that collision. Or volume. Oh, no, we're trying to find the volume.
It's okay. Because we already did it here.
No, I just wrote it down.
You can do it again.
Isn't it 1.84 for water?
That's it.
Oh. Grams.
Yeah.
J divided by 3.
I think.
We can try it. That'd be the. We'll just put it as the volume. Oh, to the ground. They wrote that on the so density.
Yeah, that's.
The amount that needs to be notified. The temperature change. Oh.
Get ready, everybody's up for it. Oh, I'll go to answer. Okay, so where should we start? You don't know. How about let's get into it, right? Let's get into it.
25.0.
So we got 25.0 grams.
Yeah, I've already took.
And that's gonna be my what in this calculation. That's gonna be my max. Okay, what's my C?
The water, 4.184.
Is it water?
Well, it says calculate the heat energy of water.
Okay, but is it gonna be the water? Where's that? There's another thing that we're missing here. We need the temperature, which we have, right? So we have.
Well, maybe it's the iron metal.
Got it. What is my initial temperature?
425.
425 degrees Fahrenheit, right? So we have to change that to
Celsius.
Celsius. How do we change that to Celsius?
We're gonna do that 500 divided by 9.
Okay, so.
Oh, no, wait, you need to get the, would you have to subtract it from the 75, subtract the finals and the initial?
Oh, we gotta change it to Celsius first. No, it's gonna be different.
What?
So you don't subtract the final from the initial, then get Celsius?
No, you gotta change it to Celsius first.
Each one individually.
You have to change it to Celsius because, well, let me think about it. Yeah,
It wouldn't be the same if you just, if you added that?
the change in temperature. I think about that. Let me think about it.
So it's just get a pass for this one, so this.
Think about it. So first thing you should always do is, if it's in Fahrenheit, you should change it to Celsius. Okay, so let's go ahead and change it to Celsius. What about you use Celsius?
The 9 divided by 5,
9 divided by 5.
5 divided by 9, sorry. Times 14, 5 minus 32.
So should that be in parentheses first?
Yes.
Because if it isn't, then we're gonna definitely have. Okay. Okay, what you guys get? How many stick figs should I have?
2.
Sure.
Yes, it's gonna be 22, right?
Okay, so let's go. 425 minus 32. So then that's gonna give me my 3 sig figs. This here, these are like 0.0000. Remember, they're exact numbers. Okay. So then 3 sig figs. Okay, what about 75? How many sig figs? 2. Work. My delta T. Final minus my initial. More minus. Okay. You guys, you there? You with me?
Yeah, can you give us more time?
And not gonna give you more time. Okay, your C. What C am I gonna use? What is the only one that I have the mass for? You guys have the mass of the metal, so why would I use water if I'm gonna be using the metal?
Well, it says calculate the heat of your.
Yeah, it does say calculate the heat of the water, right? But we know that there's transfer, right? The heat that's being transferred here has to go into where? Water. So then I could say Q water equals Q iron. Minus, right? So remember, heat's always transferred, right? Energy is transferred, right? It's going to be transferred. And it always has to be accounted for. So if I solve for Q of the iron, I can get the Q of the water. So then we have 25.0 grams times
0.40.
0.450 joules grams Celsius. And then times negative 194. That showing up over there? So my favorite thing is- So then Q ion equals 1,182.5. That's joules, right? So how many say fig should I have? 1, 2, 3. 1, 2, 3. 1, 2, 3, right? Then my answer should be okay. So then the water, I just plug this in my Q water. That's going to be 2,100. Okay. So, bam, escape.
That's it?
That's it for the first part. That's it. So the hardest part was remembering that we have to convert, change this to Celsius first, right? That's the hardest part, all right? And then remembering that if we're given the metal, we should probably use the metal.
I'll just make it be the same thing whenever you convert it after.
Because you're doing 2 steps, right? One of them is multiplication and one of them is addition. You're doing or addition subtraction, right? You're doing addition and subtraction here, and you're doing multiplication. If it was just multiplication, it would be the same thing, right? The effect would be the same. But since both of them are addition, it's addition and subtraction and multiplication, it's not the same. Okay. So like in the case of Kelvin, what was that? In the case of when we're changing Celsius to Kelvin, it doesn't make a difference because it's just one operation. It's only addition. Does that make sense? Here, since you're doing 2 operations, it's going to affect. So the more complicated it is, right, you've got to go through that step of doing the transition.
So it wouldn't directly like.
No, because it's 2 steps, right? So if you actually do the math, go ahead. Go ahead and subtract these guys and then subtract that by 32 and then multiply it by 9/5. Okay, that's what you get first, right?
Yeah.
Yeah.
I don't want to do that.
Okay, so how are we going to do this next part?
Which one, the extra credit one?
Extra credit one. Okay, I will give you an opportunity since it sounds like you guys got spanked on this first question. It's an easy question too. It's not too hard. I can make it a lot harder.
No.
Okay, what was that? This won't be on this test. It'll be on the next test. It won't be on this one. It'll be on the next one. So I will give you guys 5 minutes. 5 minutes. You guys can work in groups. Figure out the answer to the second part. Now that you guys know a little bit more, you're a little more knowledgeable. Oh, I actually have to give you. Let's assume that the water starts at 25 degrees.
180.
Hello. Okay, so now I'll also give you a little guidance. So if the water starts at 25 degrees Celsius, where is the water going to end up
So what is it? Say it again.
So if the water starts at 25 degrees Celsius, where is the water? That is, okay, hold on.
Yeah.
Let me, that does not work out very well. It's too cold. So let's say the water starts out at 2 degrees Celsius. Okay. So if the water starts off at 2 degrees Celsius, where is going to be the final temperature of the water? What's going to be the final temperature of the water? Is it going to be room temperature? After we stick this big old hot ass thing in there, right? And it's cool to whatever the iron was. So the iron was at, where did it end up? 24, right? So then that means that the water should end up at 24, right? Because it should be equilibrium, or it should be saying that, right? Okay, opportunity to get those 3 points. Yeah, cool. Okay, if you don't want it, I'll give you guys 5 minutes. You guys can discuss it among yourself, figure it out. Now I'm giving you the last part of what you need for the equation. But if you don't want it, that's all right. I mean, we can go, we can move on. I'll make sure to put something like this on the test though. Just saying.
It's a bonus that was coming out of nowhere. After we put in the water, the key into that.
These are my extras.
So when you add 24.
Oh, these are yours? You mean I can't have them? Oh, these are my extras. I can have all these. Okay, thanks.
Well, no, but that's just that part. That's just the last.
You guys chapter 6. Chapter
Yeah.
Yeah.
4 chapters. So you have chapter 6.
Oh, I'm sorry. I didn't know you meant it.
That's why I'm a little.
I know.
Maybe. Q wouldn't be 24. Q is 182. No, he's talking about the degree Celsius. Remember on the side, the initial and the final, that you did the equation on. Yeah, it has 218 and then 24. Yes. And it ended up at 24, final 24. Which is 75. You also have to do add 2 plus this as well, maybe add the 24. and it ended up at- Say also that it starts at yeah. And it is, it'll end up at 24. So would it be
24 is the
final?
number you got the line.
No, that's 24 is what I got. The water made the cube go down to 24. So obviously-
It's not funny, girl.
Yeah. Wait, what?
Oh.
Got to learn the code.
So I want to have a good day and you say, what's up, about the lunch? So I want to stress it. I know. I'm just like, I know I did that. So it's like-
That one's the G. Triangle.
So I want to get-
That's a cube.
I don't want to go to that. I'm sorry.
It's kind of, yeah.
See, I let it go. Yes. Your brain.
Like the 75 minus 32. 75 minus 32. Yeah. 613. Process.
Let's find the jewels. Shop them out. We'll convert it.
Okay, so think about what's given to you, right?
Yes, cute.
So you already have Q, right?
Yeah.
Somebody says, we got Q. So if we have Q, can I use my equation?
Well, you know, what equation is it?
Don't I have my T initial, my T final for
Yeah.
water? So T initial for water is what?
218 degrees Celsius? 2. Oh.
T initial for water? Can I erase this part here? I'm gonna keep this. So I can erase this other part here. Oh, no?
No. Let me
Got a
take a
picture?
picture of it.
Take a picture.
So.
Okay, we're ready. You good?
I was just thinking.
So now we're talking about the water, right? So we have T initial of the water is 2 degrees Celsius. It's already in Celsius, right? Okay. We want to calculate the mass. This is what we don't know. Can I calculate my delta T? Okay. So how would I calculate my delta T? Okay. 24 minus 2. So then that's what? 22. Okay. So I have my delta T. So how would I calculate my M? What was that?
Divided, right?
Divided by what? I have Q. I have Q in the water, right?
Don't you take the whole equation, like divide the C and the delta T, put it over there,
Okay, so you're saying divide this side by C delta T.
and then they'll cross out on the other side and then just
Yep.
be M by itself, right?
So we're just gonna get M by itself. That's right. You guys see that?
Where?
Where I just rearranged the equation? Okay, so we have Q equals MC delta T. Right. So if I divide this side by C delta T, I have to do it to the other side, C delta T. Right? So then the C delta T cancels out. And so I get M
Get M by itself.
equals Q over C delta T. Okay, don't I have Q?
Yes.
Don't I have C? Don't I have delta T? Okay, C for the water. This. My delta T, I just calculated up here. And my Q, we got from the other part. Okay, so you guys are learning foundation, right? But foundation needs to be applied, okay? The equation is just foundation. The concept of energy being transferred is foundation. Now you got to think about how to apply it. That means you guys got to go to that next step, right? That's something that you guys are going to have to work on, okay? Big picture, right? An application. You guys need to take it to that next level. Okay, so you can't just memorize step by step because you got to be flexible. You got to be able to move equations around, right? You guys are clear? Okay, so figure it out, give me an answer, submit it.
Oh. So 414 would be the C.
C is
Oh, okay.
Yes.
So the actual value is 4.
It's called, it's either called specific heat or specific it's represents, right? Okay, so let me kind of give you guys a little more information about specific heat. Specific heat or a specific heat capacity is, it's basically how much heat that piece of metal or that water is able to sit there and transfer. How good it is at transferring. That's always going to be a constant value, right? It does change with temperature if you notice, water versus ice, because the state changes, right? So they're going to behave differently because they're two different states, right? So if I had liquid iron, it's going to behave different than solid iron. Okay. So if you guys sit there and you think about a pan, an aluminum pan, right? So if I have an aluminum pan, whether the pan is this big or the pan is this big, its specific heat is going to be the same, right? And so that's the reason why we use that value. It's just that how much it can transfer. Okay. It's a lot, right? We talked about energy, we talked about matter, we learned to balance equations. So I'll give you guys some more problems. I haven't given any of and don't overthink it. It's a beautiful equation. It's a nice little equation that's typically given to you, right?
That's like the kiss. That's my first.
And the capital.
Okay, did you guys get an answer? Got it submitted?
That's associated with negative. Negative.
Where is that?
This is actually chapter 60.
Yes.
Yes, submitted to the disk. Sorry, chapter 50.
Let me double check.
chapter.
Level 4 is the water. Then between two on the bottom, right? And then the negative 20 and 80 on top.
So it's not
Five
this
over
over
two.
forgot
The 0.5. It's because J negative.
So you
For
want
joules
joules
is
is
negative 180.
oh, two, which is two.
Yeah. Yeah, that's why, but he was trying to find the joules of the first. So he has to get it again? No, it's right there in the primary. Oh. Okay. Right, right.
Good.
How are you guys doing?
Oh.
Yeah.
And it's four. Would be the lowest? Yeah, the vision would be the lowest.
Oh, it is. Oh my gosh.
I don't like going to more. I really don't. Like, I don't like getting out of the house. My class? Yeah, one of these. It goes pretty fast, I feel like. I don't know, I don't like it, just like an hour. Someone wants. But like, we're literally done like in 4 weeks.
Okay, everybody got it uploaded? Got your answer uploaded?
Yes, I know. Unless I.
Oh.
On the bottom. Don't look at mine. What'd you get? Just.
Did you get this?
What'd you get? Oh, like. What'd you get?
Because you know how it's cute. Because you
I would think she could just put it on water.
Yeah, but I thought that he wouldn't want us to use it. He would have not allowed us to use it. I asked you, water.
That's somebody did.
Yeah, you can see over there, so it wouldn't be,
So if you look
instead
at
of more using material there.
You have to use the whole thing.
Put a seal right here. Instead.
No, you have to, because it cancels out.
Oh.
Right? You have to use the whole thing.
Wait, what? Because I was telling them, like, if you have to do the injection, it's supposed to out. You put jewels in your thing above.
I'm not. I'm here to.
Because you have to show how you got the grant, huh?
Yeah.
Let's do 5.
Thank you.
This one.
Okay, everybody got their answer uploaded?
Yeah, it's wrong, but yeah.
Do the same like setup and same number?
But theirs is cute to one, but I don't use J.
For real.
Yeah, I don't use J. So instead of
Just
using the same-
kidding.
I use the red. It wouldn't be so.
Yeah. I'm not trying to get it 2023. That's gonna be my year.
It does, but like now you have your, now you have your proof.
Okay, you guys ready to get started?
Yeah.
Gotta get this lecture in.
The original answer where we go?
Yeah,
Finished.
I have. It just gives you the proof behind
Man, I couldn't get the end of it.
Stop at the 7-1-1.
I'm so sad.
But then you have a different answer.
I know, there was more accurate. I think it doesn't matter.
Okay, well, third time.
Okay, you guys ready?
Oh, I did.
Yeah.
Okay, everybody got this down, right?
Yeah. G at the end.
I didn't have to lose.
Okay, so let's start here. So we take a look at the different isotopes of neon, right? There are 3 isotopes of neon. One of them is 20, one of them is 21, and one of them is 22. So we have, you gotta excuse my 3rd grade handwriting, but we have neon 20. What is the number that goes at the bottom here?
Is it the top?
The atomic number, so what's the atomic number for neon? We have neon 21. And we have neon 22. This value here is going to be 90.5%. So neon 20 makes up 90.5% of all of the neon. I should probably tell you this is chapter 5. Okay. Neon 21 makes up only 25%. I mean, sorry, not 25%, 0.25%. Neon-22 makes up 9.25%. Okay, now that's going to represent a total of 100%, because we know 100% is everything, right? 100% is it all, it's all, okay? So that's going to be the whole percentage. The bulk of it is going to be 20, right? So our value, if you look at it, our value that's on the periodic table should be really close to 20. Okay, so if we actually wanted to calculate the actual value, what we see on the periodic table, it should be 20 times. Now we're going to change our percentage into a decimal form, right? So we know we multiplied it by 100. So if it's in a decimal form, it'll be 0.905. 0.905. Just divided by 100. Okay, we're going to add that to 21 multiplied by its decimal form, which is times 0.0025. And we're going to add that to the 22 times its decimal form. So it's 0.0925. Okay. And that's a 2. Okay. So if we do that math, okay. So if we look on the periodic table, what is the value that they gave you for the neon for the periodic table? So 1.18. Is there 0 after it?
Yeah.
Okay. So ours is a little off, but you kind of get the idea, right?
I know you said that.
So we just use the table. And I actually cheated because I wanted to try to get as close as possible. So I looked them up. So that one is about 90%.
Okay, so normally we'd be given the graph that would have the actual.
Yeah, they'll give you the values.
Okay.
Yeah. Or you'd have the points where you could actually clearly see the values.
That's what
We're doing a rough estimate.
Okay.
And that's also part of the reason why numbers are up there. Okay. So you guys see, so on the periodic table, the point is that the periodic table takes in consideration all the isotopes that are naturally occurring, that are stable and naturally occurring. Okay. And you guys know what I mean by stable. Yeah, so when you're talking about isotopes, isotopes have the ability to decay, right? So decay basically means that they break down, right? Like if you decay a body, right, you're breaking down that body. Okay, so isotopes, certain isotopes are more stable than others. Like for instance, carbon-13. Carbon-13 stays around for thousands and thousands of years. Have you guys heard of carbon dating? Dating. Dating, right? So it doesn't mean that carbon goes out and say, hey, baby, you know, give me your number, you know, we can go out on dinner. No, carbon dating is just using the fact that you have carbon-13 in your body or carbon-13 in something and determining the age of that something based upon how much carbon-13 they have. So carbon-13 doesn't decay. It doesn't decay very fast. It takes thousands and thousands and thousands of years to decay. So there's so much carbon-13 in the environment naturally. So as we have carbon in us, we're mainly made of carbon, right? Water and carbon, right? Those are our two major things. That's part of us. You guys have so much carbon-13 in you. As you get older and older, you're gonna have more and more and more carbon. So like trees that have been around for millions of years, they have a shitload of carbon-13 in them. And so we're able to sit there and say, oh, you're at this age because you have this much carbon-13 in you, right? So somebody who's just born is gonna have very little carbon-13. But somebody who's been around for 90 years is gonna have quite a bit of carbon-13. And so you're able to sit there and use it. And because it's slightly radioactive, it sends off a certain signal, right? As it decays, then we're able to pick up that radioactivity and say, okay, this is how much carbon-13 have in it. Okay, and we'll be talking about that in the lab primarily. Okay. So here are some example problems. What I want you guys to do is to calculate the atomic mass of boron, and we're not going to worry about the first. And let me elaborate just a little bit. So this value here, this 10.0129370 units, this is the exact value of that particular isotope. Now, we take the estimate because it's roughly for one proton and one neutron, they roughly weigh one, right? So a proton weighs one and a neutron weighs one. Now, what they actually weigh is a little bit more than one. Right? A neutron weighs a little bit more than one. And like 0.00001. And so this takes into consideration that 0.0001 that proton weighs that 0.00001 that the neutron weighs.
Yeah.
Like also more accurate. And it reduces the mass. Like that. Like the 10.0129.
Okay. Guys ready? Yeah. Look, get over to ways. You always have a choice. Just want to make right one, right? Okay, so we're gonna do this. First thing that we want to do is change this into decimals, right? So we just divide everything by 100. Divide this by 100. So then you're getting 0.199. We're going to multiply it by its mass. Plus, by this by 100. So that's going to be 0.08. And we multiply it by its mass. Okay, so if we do the math, so we get 1.99 for the first one.
8.811.
8.811.
Yes.
Okay, and add together. This guy resig fix. Fix. Add these two together, what do we get?
$10.8.
What do you guys gonna figure out too?
10.81.
So you guys see how that works?
You guys go by the math.
You can go by the mass number as well, right? You can. If you're not given the mass, go by the mass number. But if you look at the mass, this mass, pretty much the same, right? So, but if you want it to be more exact, you're gonna go by the mass. And if you really want to be exact, you sit there because the weight of a proton is defined, and the weight of a neutron is defined, and then you sit there and do it. You know how many protons and how many neutrons you have, and you can add that together. it would be, we're adding it together, just say fixed, it would be easier, right? Because there's decimal, we're adding this together, decimal here, right? So they have to use this and then use this. Okay, so it's 0. So sig fig wise, it would be 0. Okay. If we're taking into account sig fig. Okay, questions? Okay. So this is just showing you a table with different percentages of the abundance of different isotopes that actually occur in isotopes. So for instance, if we take a look here, we have the hydrogen isotopes. So we have protium and then we have deuterium. They don't show tritium because tritium is so small compared to deuterium and protium. These are the isotopes for helium. These are the isotopes for, that's mainly the isotopes for beryllium, right? 100%, right? And then these are your isotopes for carbon, right? The two major isotopes for carbon, okay? So this is just like I said, it's giving you how many different isotopes that they have and the abundance. And you guys can clearly see that, like for instance, carbon, 98.93% of it is carbon 12. Well, if you look at the mass of carbon, how much does carbon weigh on your periodic table? 12.011. So you'd assume that by looking at that number, the majority of it is going to be carbon 12, right? And so sometimes just thinking about it, like for instance, there's a question that always ends up popping up on some exam about abundance of isotopes. So if you have an isotope, let's say chlorine, right? So if we look at chlorine, 1 is 75%, 1 is 24%, right? Now, the one that's 75%, if you look at the value on a periodic table, what is the value on our periodic table? 35.45, right? So 35.45, we know that one isotope is 35, one isotope is 37. Which one do you think is going to be the most abundant? 35, because it's 35.445, right? 35.45. So the one that we assume to be the most abundant is going to be the 35, right? Which is not the case, because it's so close to 35. That value is really close to 35. Carbon 12, right, is going to be the most abundant because it's 12. The value for carbon is 12.011, right? So just by looking at it, we know that that's going to be the most abundant. If it was closer to 13, then it would be carbon 13 would be the most abundant. That's not the case, right? Does that make sense? Can you see that and see how you can just look at a problem and say, okay, this is going to be more abundant. Okay. You guys are looking at it. Crazy. Okay. So let's say we're talking about nitrogen, right? And you didn't have these values. Didn't have these values here. Actually, let me look at that. Okay, so cadmium. Okay, these are two isotopes of cadmium. Okay, so which one would you assume to be the most abundant? Cadmium 12 or cadmium 14? How many people said 12? Raise your hand. 7, 9. What else? Okay, so we have 9. How many of you guys think it's cadmium 14? Now, here's the thing, you gotta vote, right? Okay, you guys gotta understand, this is democracy, you gotta vote. Now vote. How many think it's 14? 1, 2. Okay. Now, I know I can do math, right? I'm pretty good at it. And I believe that there are 19 people in this class, right? So 2 plus 9 does not equal 19, does it? Okay, then who didn't vote? You don't vote, you get minus points. I'll figure it out too.
All right, what's the, what, you wanna ask the question?
Mhm. So the question was, which one is the most abundant isotope? Cadmium 14, 114, or cadmium 112? Okay. How many of you guys say it's cadmium 112? Raise your hand.
No, I'm gonna say it's 14. I'm gonna say 14.
Okay, that's true. Okay, so. Okay. So then we have 17.
Yeah, that's what you know.
Now, how many say it's cadmium 14? Okay. Anybody not vote? Everybody voted? Okay. So the correct answer would be cadmium 12, because what is the weight of cadmium? It's okay to be wrong. You want to be wrong today, because you don't have to be wrong tomorrow.
That's 11.
So it's 112.41. What is that closer to? Is that closer to 14 or is that closer to 12? Okay, so by default, we know that it's going to be cadmium 12 is going to be the most abundant. Okay, do you guys see how that works?
Yes.
You see the logic behind it?
Yes.
If you place it right here. No, he'll put it and it won't come in. Yeah.
Okay, so let's do it like this. Let's look at it a different way, right? We're making soup, right? And I like my soup to be a little bit of sweetness, because a little sweetness kind of, calories, right? Making chicken soup. Now, but I like my soup salty as well, right? So if I put in 2 cups of sugar and then 2 spoons of salt, two teaspoons of salt, is it going to be sweet or is it going to be salty?
Very sweet.
It's going to be very sweet, right? So what is going to be the most abundant? So it's going to be sweet because we have more sugar in there than we have salt, right? So that abundancy, the one that you're closest to, is the way it's going to be, right? So, but if I put, 2 cups of salt in there and then 2 teaspoons of sugar, it's going to be salt, right? So does that make sense?
Yes.
Abundancy is the one that we have the most of, right? Abundance. Right? So, no, ask you.
Like, what did you say? What's the-
Well, with
I
the
know
salt-
abundance is like.
Yeah. So the way that you determine which one is going to be, which isotope is going to be the most abundant is by the number. We look at the number, the one that it is closest to. It's going to be.
That's what I was trying to get. Okay, that's what I was thinking.
Okay, so let's take a 15-minute break. So I will see you guys back here in 15 minutes. I will be starting in 15 minutes. If you're not here, oh well. 15 minutes. Order day down for Starbucks.
I have my water. Yeah.
Okay, so let's go ahead and start talking about the periodic table. You guys are already familiar with the periodic table, right? You already know what the atomic number is.
Oh, right.
About periodic table, sure.
I'm not
Okay, yes, that is actually a very good question. So let's actually take a look at our periodic table and then I'll explain it. Okay, so in the old days, they separated in terms of group B and group A and group B. Okay. Group A consisted of one, group 1 through 2, group 13, 14, 15, 16, 17, and 18. Group B consisted of all the other stuff that was removed, right? So when I learned chemistry in college, they started us out with just group A, right? Because it all makes sense. This guy uses 1 electron for gas, this guy uses 2. When you get down here, it doesn't make sense anymore because they're transitional metals and they don't behave the way they expect them to behave, right? And so they understood better group 1 metals, or group A, the main, right? Which is 1, 2, 13, 14, 15, 16, 17, 18, right? So then it would just be, this would be 1A, this would be 2A, this would be 3A, this would be 4A, this would be 5A, this would be 6A. Okay, so, but again, that's the way it used to be done, right? And it was only done that way in the US. It went internationally, just numbered completely across. And so we've started to adapt that same method because we also have a better understanding of the transitional metals, right? And we are starting to introduce you guys to the transitional metals rather than just ignoring them. Okay. And the other thing is because it's also based upon noble gases in their outer shell have a total of 8 electrons that fill that outer shell. Okay, so that farther shell, and we'll talk more about that when we get to chapter 11. We're going to get there pretty fast. And what it basically means is that if you come across it's 1, 2, 3, 4, 5, 6, 7, 8, right? So those 8 groups, that main group, represents that 8 valence shells, that outer shell. Okay, and again, we'll talk more about that, how that is going to be important. 8 is like this magic number. It's stable, right? And so if you have 8 electrons, valence electrons surrounding you, you're basically stable. You're in a stable state, right? That's like the noble gases. You're like the noble gases. And we'll, like I said, we'll talk more about that later on. But for right now, just know that the main group A would be just 1, 2, 13, 14, 15, 16, 17. Yeah, would be all the stuff in between. So, and the other thing that I want to show you now that I have everybody here is that the periodic table really looks like this. It's going to be more important when we get to chapter 11. This is what the periodic table really looks like. The reason why we shorten it is to make it easier for us to get it on a single piece of paper, compared to this. If you guys take a look, the lactanoids, these guys, and the actinoids, all of these guys are between groups 1 and group 3. They really belong in this area. Okay. So this is what the periodic table really looks like. But as you guys can see, you can't get the full thing on the screen, so it makes it hard to see it that way. So we make it simple. So where we just use that as a placeholder where they would be. Okay. And so then that way we can get it all on the same screen and we can actually see all the elements rather than having it flipping through pages. Okay. So let's talk about the periodic table. Segment.
Do you have an extra copy of the periodic table?
I do.
I just need to take charge. Thank you.
Okay, so initially, the periodic table was arranged by mass, right? And when it arranged by mass, it kind of screwed things up. So that's the reason why we started using the atomic number. The atomic number helps us get really organized, but there are certain cases where one atom may have more protons, but it weighs less than another atom, right? So this is currently what the periodic table looks like. As you guys can see, this is that group, main group A, and then this is our subgroup or our B group down here, right? So it goes A1, A2, A3, A4, A5, A6, A7, A8. Now that's the old way of doing things, right? So now we just number it straight from 1 to 18. So we have everything incorporated to 1 to 18. Okay. So a lot of times when you have a question, some of the questions that they'll ask you, they'll say so 3 is in group 3A/13. And so that's how they ask the question. So you know that group A, you could just kind of ignore that part, look at 13. Okay. Do you guys understand that?
Yes.
Okay. So we've already talked about the atomic number. We know about the nuclear symbol, and we've already talked about the atomic mass. You guys are very familiar with the period. We go back to the table. Numbers that are here are the period, right? Again, old periodic table, they didn't have the periods at that point, right? So, but now we incorporate that. You guys have the periods on the sides. Now those periods represent the energy level, right? So as we go down further, the higher the energy level it is, right? So something like francium is going to be, more reactive and stuff like that. It's also at a higher energy level. Okay, and because it's at a higher energy level, it wants to try to get shut down. Okay? It also means that it's going to be bigger in size. And if you go down the periodic table, it gets bigger in size because those energy levels, the way it works is that that first energy level, then it has a second energy level, then a third energy level, and then a fourth, and it just gets bigger and bigger and bigger. Have you guys ever seen the Russian dolls?
Yeah.
Where you have a doll within a doll within a doll within a doll. So these periods kind of are like that Russian doll. So that's the very first doll. This is the first doll, and then the second doll. Then it's the first doll, second doll, the third doll, right? And so you just have layers and layers that are being added on for each of those elements. You go down the periodic table. Okay, you guys kind of understand that. You kind of see what I'm getting to. So we've talked about the main group. Main group is group 1, 2, 13, 14, 15. That A group, that's considered the main group. Now, the reason why they're considered the main groups is because those are the ones that we think about when we're talking about reactions and things. And that was the thing that most people would try to use for everything, right? They would kind of avoid those, except for if you're in material science, they would avoid those metals, those transitional metals, because they didn't know how exactly they were going to behave in reaction. Because they were changing. So we talked about the transitional metals or transitional elements. Right? We've talked about metal and metalloids. So let's take a look at the periodic table again. Okay, so look at our metals. If you select on your P table, this highlights all of the metals. We know that all of the non-metals, right? We know that our transitional metals are transitional metals. These guys are called post-transitional metals. These guys are here. Okay, so they're also transitional metals. They're considered post-transitional metals because they're beyond that metal, right? Or you could draw that line for metals, right? So these are called post-transitional metals. These guys are metalloids. These are our non-metals. Those are our noble gases. So these are the halogens. These are the halogens. These are the pigments. These guys like to react. Halogens are going to be very reactive. Chalcogens are going to be slightly less reactive, and then the picogens are going to be less reactive. Okay, so you'll see a problem something like this, where it says, list the atomic number, the chemical symbol, the atomic mass of the third period element in group 6A/16. So you just ignore the 6A. So what's in the third period and in the 16th group? Sulfur. So then we just write sulfur, right? So what's the atomic number for sulfur? 16. Atomic number is 16. Its atomic mass.
32.06.
Okay. So, and based upon that number, what would you assume? Is there an isotope? Are there more than one isotope for sulfur? Yeah, I would assume that there would be more than one isotope. So,
Oh, wait, wait.
it was the okay. So, is it a metal, a non-metal, or a metal?
It's a,
It's a non-metal. Okay, so these are the more common elements. You should know these, right? And the way that you know them is by using the periodic table. You should know each of all of the common metals, right? You should be familiar with the symbol. You should know them off the back of your head, right? Okay. And the way you know them, I don't expect you to know that, but the way that you should know them, and you should definitely know carbon. You should know everything about carbon. Carbon is like your best friend. If you don't know carbon enough, that's it, period. So, symbol for carbon?
C.
Okay. What is the atomic number for carbon? What is the atomic mass of carbon?
12.12.
So, these are the ones that are most common. Okay, let's get to chapter 20.
I skip it.
Okay. So we've talked about isotopes. You guys are very familiar with isotopes. One thing that I want to remind you is that a lot of the isotopes that we have talked about, they're stable, but they do decay, which basically means that they're very stable. If it's unstable, it's gonna be considered what we call radioactive. That means that it will decay at a very fast, typically a fast rate or a spontaneous emission type of situation. Okay, now nuclear chemistry is going to be based upon the action of the atomic nuclei. So this is the thing that I should probably talk about it briefly. So in the nucleus, now electrons.
I'm sorry. You put it so we can see it up there. We have to.
Yeah. I'll do that. I keep forgetting. Thank you for reminding me. Okay, so electrons are going to sit out here and they're going to circle the nucleus. So they're going to orbit. It's kind of like the Earth orbits the sun. Okay, so or like the planets orbit the sun. Okay, so at the center of the atom is the nucleus. Nucleus is the biggest part of the atom, but what makes it an atom much bigger and grow is the more electrons that it has orbiting. Now, we know that electrons are really tiny, right? They're small in size, and they're also tiny in weight. And they're constantly moving, constantly moving. Okay, so they're constantly moving, and your protons and neutrons are going to be here in the center. Okay. Now, when we talk about nuclear chemistry, we're looking at chemistry that is going to be affecting the nucleus of the atom, right? So we're going to be playing with the nuclear part. Okay. So when we talk about radiation, radiation is just going to be the emission of rays or particles. Now I'm going to distinguish between rays and particles. So you guys remember when we started, we talked about micro, macro, and particulate. We also talked about gamma rays. Right? Did we talk about gamma rays? Did we talk about gamma rays? Okay, so let me talk about gamma rays. Actually. It's the problem when you get ahead of yourself. Okay, so this here is what we call the electromagnetic spectrum. The electromagnetic spectrum is basically it's waves of energy. And if we take a look at our electromagnetic spectrum, we have what we call gamma rays. You guys know the incredible thing. Anybody heard of the incredible thing? So anybody know the origin of the incredible thing?
You guys start from gamma.
Gamma rays, right? Yeah. So gamma rays are these really small rays of energy, right? They supposedly penetrated him, and he was kind of like special in a way that they didn't destroy it. Gamma rays are so small that it would destroy your DNA. If you get high exposure to gamma rays, it destroys your DNA because it breaks up your DNA. Right? So long exposure to gamma rays would be death to us. Right? And so, and again, it's waves of energy. And so they're so small, those waves of energy are so small that they go through your cells and they are able to damage your DNA. And so we need to be protected from gamma rays, right? So X-rays, they're a little bit bigger than gamma rays, right? Now, they're about the size of an atom or so. So X-rays also can destroy our DNA, because if you think about an atom, DNA is basically made up of lots and lots of molecules and stuff added together. But they're so small that they could actually damage. So that's the reason why we have to wear those lead shields to protect us from those rays when we go to the doctor. You guys get X-rays done on your arm and stuff like that. If you guys are constantly getting X-rays all the time, or getting exposed to X-rays all the time, then you would be damaging your DNA. You end up getting cancer, or you just kill the cells completely, right? UV light. Why do they tell you guys to, you're supposed to use sunscreen? Why are you supposed to use sunscreen?
Cancer, right?
Because you can get cancer. Why do you think you could get cancer?
Right?
Because the UV rays, right? So the UV rays are so small that they actually do the same thing. They will damage your DNA.
Your
But-
eye, but look, I thought it's like mainly your eyes though, right?
No, it's not your eyes. It will affect your eyes, but skin cancer. Most people will get skin cancer. So people that lack melatonin, melatonin is a natural inhibitor of those UV lights.
So did you
So-
say melatonin too, please?
What was that? So, so typically people who lack melatonin or have low levels of melatonin are at high risk of skin cancer. So you're always encouraged to wear sunscreen all the time because you would be at high risk of skin cancer. Okay, so, and that's again because those waves are so small that they can cause damage to your cells, which would also damage parts of your DNA. They're not so small that they would shred it up to pieces, but they would cause large chunks of destroyed. Often, when they're doing cleaning of things, right? If they're trying to get rid of viruses, they're trying to get rid of bacteria, they use UV light to sit there and do that because it does damage those cells or damage the DNA that's in the RNA. Okay. This here's visible spectrum, right? That's the light that we white light. Okay, so white light, if you put it all together, is composed of all of these different colors. That's white light. We break them up, we use a diffraction slide or something like that that's able to break it up, or we use filters, you can see the individual different colors. We'll do that later on. Sometime next week. Okay. Now, these represent waves, again, of energy. Electromagnetic waves are just kind of waves of energy. And they all are going to be traveling at the speed of light. Okay. Now, the difference between each of these waves is going to be the wavelength, the distance of from top to bottom of that wave from top to bottom. That's the wavelength. So these guys are going to have a small wavelength. These guys are going to have a long wavelength. So we start talking about radio waves. Radio waves, which is energy, right? Translated through the air, again in that wave pattern. But they're going to be so big compared to what we see in terms of the gamma rays. Okay, you guys with me so far?
Yes.
Okay. Okay. So we have what we call alpha particles, beta particles, and gamma particles or gamma rays. So alpha particles are just going to be, we talked about helium, right? So our alpha particle, and then also write it up here, in addition to writing it up there. And then I'll show it on the screen in a second. Okay, so alpha particles are just going to be the release of helium, of a helium atom. So that's what it boils down to, the release of a helium atom. Now, alpha particles are considered to be high energy, right? They're going to be high energy, but it's going to be high energy that's going to have a positive charge associated. Okay, so it's going to have a positive charge associated. This is symbol for alpha. Okay. Yeah, have beta particles. Beta. So beta particles are just going to be an electron. Okay. So we know that electrons are positively charged or negatively charged. Negatively charged. Okay. Okay. So this guy is going to be negatively charged. And then we have gamma. Well, gamma rays are gamma rays. They're just the whole rays that are being emitted. Now, gamma rays, again, are going to be worse than anything else. Alpha particles are not going to be too bad for you. Beta particles, they can be pretty bad for you because they cause things to react and cause issues if you get high exposure to beta particles. Gamma rays are going to be the ones that are going to be worse, depending on how many gamma rays are emitted from the source. Okay. Okay, so this is the symbol for gamma. Okay, alpha, beta, gamma. Now, if we think about the electron isn't going to add anything. It's not going to add any protons, and it's not going to add anything. So it's going to have 2 zeros that are in the system. The only thing it's going to add is a negative charge. Right? I'm going to
Is it
revise
always
this.
a negative charge only? Always?
Electrons,
Well,
Tell me.
no, with beta particles.
beta particles are always going to be negative. It's going to have
Yeah.
a negative charge associated with it. So, but the thing is, that's going to be different. This guy is going to be emitted. Some way we're going to emit this from our nucleus. I'm going to talk to you about how we're going to get that. Are you guys with me so far? Not too bad. Just definitions.
Whew.
Okay. Okay, so this is just showing us the different charges. So I told you beta is negative. So if beta is negative, it's going to go towards that positive, right? If alpha is positive, it's going to go towards the negative. And gamma is not going to have any preference to either one, so it's going to shoot straight through. Okay, so if we have a charged plate, positive charge, so our beta particles are going to go towards positive charge because it's negative, right? Does that make sense? Because opposites attract, right? Alpha particles are going to go towards the negative because they're positive. Gamma isn't going to have any preference because it has no charge associated.
So it just stays straight.
It just goes straight. Yep. Okay. So if I put two negative things together, what happens?
They go opposite. Repel, right?
They repel. That's right. They're going to go opposite. So we kind of think about it. We have a positive, a negative, a positive and a negative plate, right? And we put particles that are beta particles through here. Well, this one is going to be pushing it towards that positive direction, right? As well, because it's pushing. So we're going to get two effects. Okay. So today, this is what we're going to be looking at. We're going to look at shielding. So we're going to be looking to see whether the radioactive particles are going to be able to shield. So alpha particles, they're basically, they can be blocked by paper, right? So it doesn't take much to block. Beta particles, well, they can't be blocked by paper. They can only be blocked by lead. Gamma particles, they can't really be blocked by a small piece of lead. You've got to use something that's pretty thick to sit there and block those gamma particles. So again, which one do you think is going to do the most damage?
Yeah.
Okay, it's the hole, right? So. Now, the way that we detect radiation, okay, is by using various types of instruments. You can use, well, a couple. We use film, right? So we get radiation and we expose it to film, or that radiation expose it. Then basically what will happen is it'll turn that area that's black. So the UV light that's emitted in the air actually has forms of radiation. That's part of the reason why, have you guys ever opened the back of a camera to the light before you close off the film? Let's ever get that.
Yeah,
Done that before, what happens?
it damages it, it like changes colors, right?
It doesn't change colors. It makes it all black, right? The reason why it makes it all black is because you basically expose the film to sunlight, right? Or UV radiation.
But isn't it brown and it turns to black, right? If that is it, right?
Yeah, that's right. It'll be, well, I guess it does change the color black. That's the only color it changes, right? So you have totally black film with no images on it, right? So one way that we could sit there and test whether radiation is present is by using film. Okay. So another way is using what they call a cloud chamber, right? And so basically it's using saturated vapors, and the fact that you have saturated vapors and air that is there is going to cause those vapors to separate. Okay, so if you have radiation present, you'll see the separation of the vapors. Okay, the other ways are instrumentations like a Geiger counter, right? Geiger Mueller counter, scintillation counter, and a gamma counter scanner. This is just kind of tells you how they work. So basically, your radiation source is going to be exposed to the film, and then you're going to get a little spot on the film showing where that radiation is at. So often we use this in science. So we'll use radiation to sit there and label like protein. Let's say we're looking at your metabolism. We'll sit there and have you eat a little bit of radioactivity, and then look at your food, see how well you're metabolizing. Right? If you have a lot of radiation good, then it's going to keep your system. So that means you're not incorporating the way that you should. It's effectively happening. Right? So that's one way to do it. So have you guys ever, any of you guys have had your metabolism checked? They had you drink that big old bottle of donkey stuff?
It wasn't a bottle.
It wasn't a bottle? Okay. So you guys, any of you guys have to get any labs done where you had to drink, it's like, it tastes like milk and magnesia?
I had to get a glucose test before.
This test before?
When I was
Big old
pregnant, I
styrofoam
had
container?
When I was pregnant?
One of the diabetic tests is
Yeah,
that
that's
they
what it
do, is actually uses radioactive material. But they'll have you drink a big old thing of solution first before you get the test done. Yeah,
Yep.
so that's essentially what's happening there. So they're incorporating that into your body. They're seeing how much of it is being maintained in your body and how much of it is being released. So they're seeing how much glucose you're actually utilizing and how much is being disposed. Okay, so let's see. So this kind of gives you the idea of how these instruments are used. So like the Geiger counter basically is used to detect radioactivity, and literally all it is a counter that goes as soon as it comes across radioactivity. You guys are going to use something that's very similar to the Geiger counter. Simulation counter is basically you're looking at the fluorescence of a compound. So you basically put sample that you believe to be radioactive in a solution, and then it's going to fluoresce, and you pick up that fluorescence. That light is being emitted as a result. This is an example of a Geiger counter. You guys, like I said, you guys are going to do something very similar to this today. This is a scintillation counter. It's this huge piece of equipment. It's a big footprint. Literally, it's going to be about the size of this table. Takes about. So this here is a gamma camera scanner. So this is what you guys will run into in the hospital. So we talked about isotopes. Now we call them radial isotopes because they're radioactive. Right? So we have our naturally occurring isotopes, and we also have what we call radioactive. So we use radioisotopes for various things in health. Often we will use radiation therapies if they're indicative of cancer, right? Kill tissues, right? So the way that we measure them is called in RIMS. And so this is a unit of determining how much radioactive dosage that you have in the body. So dosage that exceed 600 RIMS are going to be fatal. The sources of radiation are basically everything, right? Rock, soil, water, atoms, the cosmos. These are the different types of radiation. So we have 92% of it occurs naturally. So those are our isotopes that we've talked about. Okay. Then we have the stuff that we use for medical x-rays, which is about 11%. We have 4% in nuclear medicine. We have stuff that we consume, like our makeup and the mask that we use and stuff like that. Anybody use masks, right? Some of that has radioactivity in it. So low levels help you stay young, beautiful, right? Okay, and then we have 18% of it that's going to be man-made. And then we have this small amount here that we use for nuclear fuel and stuff like that. So when we're working with radioactivity, we have to calculate what we call the half-life. So the half-life represents the time that's required to get half of the radioactivity of that sample. Okay. So let's say every specific type of radioactivity has a specific half-life associated. So remember when I was talking about carbon-13, right? And I said it takes forever for it to decay. Well, carbon-13's half-life is like thousands of years, right? Where that means it takes thousands of years just to get to the point where it's half gone in terms of its radioactivity. Okay. So the way that you calculate its half-life is R is going to represent the amount that remains after in number of half-lives. Half-life is like half the life that it has. S is the starting quantity, and so it's 1/2 to the nth power. That's the number of half. So let me give you an example. So it makes sense. Okay. So the half-life of bismuth 210 is 5 days. Okay. So we have our equation, which is R equals S 1/2. Okay, so we know that bismuth it's half-life. Okay. So if you're starting out with 16 grams, so our S, you have 16 grams of bismuth, how many grams would you have left after 25 days? 25 days. Okay. So if we wanted to calculate our N, So one half-life is just 5 days. How many half-life are in 25 days? How would I figure that out? Simple. And 25 days divided by 5. So that would be 5 half-lives, right? So then I would just plug this into my value. My S is 16 grams, so 16 times 1 over 2 to the 5th power. So that would be 2 times 2 times 2 times 2. So that's 2, 4, that's 8, that's 16, that's 32. So then I have 16 divided by 32. And that would be 5. Say this. Okay. Piece of cake. Oh, let me. Sorry.
So basically you say 16 times 2, that's 32, 16 divided, right?
It's 16 times 1 over 2, right? But it's to the 5th power, right? So if you take 2 to the 5th power, what would that be? 2 times 2, so that's 4. So that's 4 times 2, which is 8. And that's 8 times 2 is 16. And then yeah, because 1 to the n power is always going to be 1. It doesn't matter what it is, right? 0 is going to be 1. 10 is going to be 1. Gotcha. Oops, that did not work, did it? Here. That help? Okay, so that's how we would calculate the half-life. I mean, the amount that we remain. So typically half-lives are going to be given to you, but if they tell you, they're like, okay, so you're starting out with, you ended up with this amount, and you started out with this amount, right? And you have this many cycles that happen over this many days, then you can calculate the half-life, right? Because you know that it's going to be your time that you're given divided by your half-life. Right? So n equals given time divided by half. Okay. Equal half. Okay.
Can we do another one of those problems?
Sure.
That's
So noon to 3 o'clock. 3 hours? Yeah. So, and we have our half-life in what? 18 minutes, so it's a minute. No, to change 3 hours to minutes. Minutes. Yeah, 180 minutes. Ethan?
So minutes are at the,
In the dance. I know you guys can't see everything.
we got to worry about sick days, right?
Yeah, we gotta worry about sick days. Sick days that happen. Two. And then my answer.
21.
Okay, questions? questions? Plugging it in. Okay. So you guys ready for the next part? So don't judge me.
Yeah.
Not judging you.
I'm a little slow. Well, I'm still on attached. I wrote this one, I really-
Okay. So we talked about carbon dating, right? What was that? We talked about it earlier. Carbon dating. Can somebody remind me what carbon dating was? Let's say it again.
They have a little bit when they're older.
That's right. Okay, so they're looking at the ratio. In this case, they're looking at the ratio of carbon 14 to the carbon 12. So carbon 12 is the one that is the most abundant, right? And as we get older, the older you are, the longer you've been on this planet, you're going to have more and more carbon 14 in you. And it takes forever for carbon 14 to decay. And so we use that ratio that you have to determine how old things are, the age of things, right? So that's radiocarbon dating or carbon dating. Okay. Remember I made the joke about carbon saying, hey, baby, you know, just a few minutes ago. You don't remember that? Okay. So let's get into some more terminology. Nuclear chemistry has a lot of terminology. Too much calculations. Okay, so when we think about nuclear reactions, a lot of nuclear reactions are decay series, meaning that we go from one stable compound to the next stable compound to the next stable compound. And so you're just going to be breaking down until you reach something that's going to end up being stable, right? So I'll show you an example in a second. Okay. So uranium. You guys heard of uranium? What is uranium used for? Does anybody know? They're used for bombs. They're used for bombs, or they're used for nuclear energy. The reason why we use uranium is because uranium is naturally radioactive. It's very, very radioactive. And so it starts off not stable. So uranium, and this is 33, uranium 33, well, it's going to break down. It takes 10 to the 1,000 years to break down. So this is the isotope. This is the time it takes its half-life, its decay. Okay, and then it'll break down to thorium, and then that'll break down to PA, and then that'll break back down to uranium, and then it breaks down further and further and further, and so then you just keep going until you get a stable form. Now, all these other forms are not stable, so they're going to decay. Over time, they're going to decay. Okay. Now, one of the benefits of using uranium is that we can play with it. We can actually shoot it with neutrons or shoot it with protons to sit there, or alpha particles, to sit there and cause it to be split, and we can get a lot of energy from it. And that's what we're going to be talking mainly about. But naturally, it takes a while for uranium to start to decay, but it does decay, and it decays quite a bit. It's pretty strong in its decay. Okay, are you guys getting what I mean by series of decay? So you'll start off at one element that's unstable, and it will keep going until it reaches a form of being stable, meaning that it won't decay. Okay, so here's an example of a nuclear equation. And this is the thing that I want you guys to pay attention to. So you guys know how to write the nuclear symbols, right? So in this case, we have uranium. Okay, so we have uranium. If you guys take a look, when it's broken down, in this case, it breaks down to an alpha particle and the radium, right? So if you take a look at the alpha particle, so the alpha particle is always going to be helium, 4 up top, and it's going to be 2 where it's atomic number, right?
Is it always gonna be helium?
Always alpha particles, always going to be the helium atom, right? So if they say, if you read a problem and they say that alpha particles are emitted, right? You want to know immediately what's going to be emitted? Helium, or helium atom, right? So then that means we're always going to write it as 4 to helium, right? And then you just subtract off what's ever left. So if this is 4 minus 238 is what?
34.
234. 2 minus 92 is what? 90, right? And so you look at what's 90. If you look at the periodic table, what has atomic number of 90? Thorium, right? So thorium has the atomic number of 90, right? So we know that TH is going to be that element. Okay, so here, thorium is going to be broken down into a beta particle. So let me correct my writing. Earlier I said
So
E, down the limit as like that, E minus. Okay. Okay, so then a beta particle, this is going to be how a beta particle is going to be written. Okay, for this chemical reaction. So then we'll go 90. We know that it's going to be E minus. So then we'll minus. So then that means that we go to 91, right?
did you add one, right? Oh, you subtract.
You're technically subtracting the negative, right? The negative value, right? So if you're subtracting the negative value, then yeah. Okay, so then we know that this will be 91. So what is the atomic number for 91? For actinium? Okay, so for actinium is going to be our isotope. And then we know that electrons don't affect the mass, right? So then we just move that mass over. Okay.
So thorium, so when it goes into a beta particle, that was the
Beta particle, this is going to be the symbol for beta particles. This is how we write it so that we keep track of.
Earlier, I think you
I-
confused everyone.
Yeah, because I wrote it like this.
You wrote it too.
Because, yes, and I wrote the negative up here, right? Right? Because in regular chemistry, this is how it's like this.
because it really doesn't matter.
That's right. Or we'll just write it like this, right? Okay, so the negative in this case, we'll take into consideration. That's right. Yep. Okay, and again, this is because it's affecting only the nucleus. Okay, so it's affecting only the nucleus. So this, we're talking about these particles, they're affecting the nucleus. That's why we have to write it as that negative one, affecting the nucleus. The atomic number, which is going to be affected. Okay. Are you guys with me so far?
Yes.
Okay, not too bad? Not bad at all, right? Okay, so write the nuclear equation for the emission of a beta particle from bismuth to CHM. No, it tells you what's being emitted, what is being emitted. Emitted means that, or emission means it's being let loose, right? So that means that that's gonna be on the other side of the reaction, right? So what does a beta particle look like?
Like that, like the 0.
It looks like this? Yeah. Okay. Okay, so then what's going to be left over?
P
210.
34.
You're gonna put the PI for the symbol plus.
Okay, what's going to be the symbol?
Yeah.
Not too bad. Yes, sir. That was made. Yeah, so the ones that are in parentheses, so those guys aren't stable, right? So those are obviously, so we generated those. So they decided, okay, so these guys are going to be elements, even though they don't have these. So the reason why they're in parentheses is because I'm not quite sure about how many neutrons. Okay. And I think it was done in Livermore Labs, so. Yes, so,
Oh, no, no, I looked at two. Because we had that talk last.
that's right. Yep. Okay, how are you guys doing so far?
So, what did you guys?
Yeah, so what happens is that you're moving over one, right? Because that's why you're taking into account that minus. So you're saying that a beta particle is being emitted. So then that means that this guy's gonna be a -1. So that means you got to move over one, right? To account for that. So if you add these together, they add up to that -2. Right? -1 plus 84. That's up to 82.
I was trying so hard to be a noble gas. That's how we.
Well, it's nuts. These are a little different. And that's the thing about nuclear. Nuclear is a little funny, right? They're just trying to get stable, right? They're just trying to find a way of being stable. And so what they're going to do is like, if, let's say, polonium 210, if that isn't stable, then it'll break down even further, right? And then it'll break down further until it gets to the point that it's stable. So you'll get to K until you get to something that's stable. Okay, so now here are the things that are going to be different between a chemical reaction and a nuclear reaction. So a chemical reaction, okay, so chemical properties of isotopes and isotopes of elements are going to be similar. So those elements are going to behave similar, even though they're isotopes. Now nuclear property, right? The isotopes, oh, they're going to be different, right? Yeah, they're going to be different. They're going to behave different, right? So if it's unstable, then it's going to decay. It's going to cause issues, right? It's going to get radiation. Right? Okay, so chemical properties depending only on the electrons outside of the nucleus, where nuclear activity is dependent on the chemical combination of both electrons and protons. Everything. And then, so atoms are going to keep their identity, but they're going to change compounds, right? Where here, we're going to end up resulting in different elements, right? Because we went from bismuth, boom. Yes, yes, definitely the major thing is right there. Okay, and in terms of the amount of energy, the energy that's going to be emitted or that's going to be needed for this to happen is really low for chemical reactions. relatively speaking, but crazy high. And so it's amazing to me that in the US, we have, I think there's 2 nuclear plants in the US. Nuclear energy is the most abundant energy. We are so fuel heavy, we rely solely on fossil fuels, right? More so than any other country, which is ridiculous because we have, let's start it off. The technology was mastered here, right? In terms of nuclear engineering. It was mastered in the US, even though it was imported from other scientists. But it was mastered. We learned how to master it and how to obtain it. And yet we have the least amount of it. Do you guys want to know why? No, it's not because we like to make money. It has nothing to do with us making money, because in the long run, it's hurting us. But we're not making money off it. It's because the oil lobbyists. The oil lobbyists get a lot of money to energy. Hey, scare people from getting started. You know, oh, what happens if you get oil? What happens if you want to get oil? Same thing, same issues, right? But the problem is that we're so heavily reliant on fossil fuels that the oil companies, Shell, Arco, those guys, they just kind of monopolize the system, and so we won't make that transition. So it's kind of interesting because we're behind compared to the others. Although we were the ones that developed the technology, and we also sell a lot of the stuff to contain the technology. We make money for other places, but we're hurting ourselves because we pay so much money for energy. Okay, so, and I shouldn't say that because, you know, what is it? Arrow gives us a lot of money. They give our campus quite a bit of money, not science department. So until they start giving me money, then I'm still gonna talk shit. So, they still didn't. But anyway, let's move on. So nuclear bombardment. So this is the concept of basically adding an alpha particle. So we're going to introduce an alpha particle to an isotope. So a lot of times this is artificial. This is what they do in Lawrence Livermore labs down up north, and they do it in Arizona. And so we have, like I said, we've been developing this technology. We use it on nuclear reactors on submarines. We use it for war purposes, but we don't use it to sit there and do the and also on some of the ships. How many of you guys are associated with the military? Your husband got on the boat?
Yeah.
Ask him how much of it, how many boats currently are nuclear powered? There's a few of them there. So we take advantage of it in wartime situations. We would take advantage of it. So in this case, if we're introducing an alpha particle, what's being released here? We're getting a neutron, right? And so this is the symbol for how we write a neutron in the case of nuclear engineering. The neutrons are going to be in one. Oh, so why do you guys think it's going to be in one? Why is one going to be on the top? Like because
Electrons won't change.
electrons are going to change, and so we know that they're not going to have a part in that anyway, right?
But maybe.
And so what's up top? What's up top and to the left? Yeah. The what?
The mass.
The mass, that's right, the mass. The mass is up top, right? So we know that this makes reference to the mass. So neutrons only affect what? The mass. So it affects the mass of the atom, right? So that's the reason why we write a neutron. Okay? How are you guys doing so far? So if we said a proton is added, then how would we do that? Or actually, one more, right? Because it affects the mass and the that's the way. Questions? Cash? Like,
Cash.
So that's this example.
no, we're adding an alpha particle. So we're adding an alpha particle. So if an alpha particle is being added, then in this case, what we're getting is, we add these two together, right? 6, right? So then we know that we look at 6, we know that that's carbon. And then the most stable form of carbon is carbon 12. We want something that's going to be stable, so that's how we get carbon 12, right? And then these two have to add up, right? So that's 13. So if we have carbon 12, our stable form, so then that means that we're getting a neutron that's going to be emitted.
So in the sense of trying to carbon 13, carbon 13 would stabilize.
That's right.
So then it would end up.
And then we end up with carbon 12. Okay, so if we look at it, these tops on the other side of the reaction, they add up, right? So in a sense, it kind of works out the same way. What we put in, we've got to get out. Here we put in 6, we got out 6. Here we put in 13, we got out 13. Okay, not quite the way that we would expect it to, but okay. Okay, so at Lawrence Livermore, they have a particle accelerator. Right. So basically what they're saying is that they're putting a particle and they're bombarding nuclei, right? So remember when I told you that they make compounds? That's how they make compounds. They just basically add particles to sit there. So if you guys take a look, it says elements whose atomic numbers that are greater than 92. So those are all manufactured elements. So if you guys take a look, all the ones that are above 92, you notice they're all in parentheses, right? Okay. Okay, so radial isotopes, they're going to be used in medicine. We use them for battery powered and smoke detectors. We use it in food preservation. We use it in tons and tons of industries, such as semiconductor industries, medical industries, pharmaceuticals. We use it in scientific research. We use it in archaeology. We even use it in terms of studying water. Smoke detector. This is basically has to be used as a smoke detector. So here's your radioactive source, and so it causes the decay, and then as a result of the ions that are forming, and it's going to be able to sit there and detect whether or not you have carbon monoxide or smoke. Yes. Okay, so this is an example of fission. So fission is the splitting of an atom. So in other words, we're going to be bombarding it with neutron. Shoot it in a neutron, and we're going to cause the atom to split. So if we split this uranium with a neutron, we get strontium, 94, and then we get xenon, 139, and then we're going to end up with 3 neutrons. Again, if we add them all up, they should all add up to the same size. So altogether, this mass should be 136, 92. Well, we had 38 plus 54 is what? 92. 94 plus 139. 5 plus 1. There's 3 of them. That 35. 94 plus 135. 2, 33, 32, 33, right? And then we add 3 more, Right? So that should be 236, 235 plus 1, 236. Okay. What was that? Yep. At the end of the day, what you put in, you gotta get out. It has to be accounted for, right?
So it's like balancing equations.
It is like balancing equations, but now we're talking about nuclear equations.
That was it.
What was that?
Now the law makes sense.
Now it makes sense, yeah.
At first it was just like there.
Okay. So, and this is just showing you chain reaction. So we'll start off with one, it'll break down, and then as a result, we'll end up getting more and more reactions. Same thing that we showed you earlier. Okay, so again, this is where we get some more nuclear power. So we can get it through fission. Fission is what again? Splitting. Okay, so it's going to fission, it's going to be splitting. So this is an example of what a plant looks like. So pros and cons. Pros and cons of nuclear energy. Right? Well, we get a shitload of energy per unit mass. There are no greenhouse effects, so we don't get the carbon dioxide that we're getting in the environment. There's also, we don't have to worry about trying to buy gas. The cons, well, there's always the threat of accidents of radiation. Radioactive waste is very problematic because we know that it emits particles. Right? And then if it's not done responsibly, we cause a shitload of problems in the world. Right? Okay, so here, this kind of gives you an idea of where everyone is in terms of electricity from nuclear power. So we're right here in the middle. There are some that are below us, but a lot of us are above us. Now, I'll also have to say this table is probably 2006 is when it was copyrighted. This is probably older than that. They probably used this in 2000. The numbers have changed quite a bit. A lot of these countries, such as China, are above us now because they recognize the power of nuclear and the fact that we're often dictated by money, the industries that are currently ruling the country, more so than anything else, and so that plays a huge part in our decisions. So we also have what we call nuclear fusion. Now, fusion is adding two together. Now, they've been playing with the fusion engine in terms of car development. It would be incredible if we get the fusion engine, hydrogen fusion engine up and running. It would be incredible. It would change things, you know, in terms of power that's associated with it. You know, just by doing one action, you sit there and power your car from here back to New York and back 2 times off of one reaction. So it would be incredible the amount of money that could be saved, right? But again, we love oil, right? We need our oil. So that's part of our problem. We're so stuck in our oil components. So this is an example of fusion. Fusion is the addition of 2 things together. So in this case, this is deuterium, and this is deuterium and tritium. We add them together, we're going to get our helium, and we're going to get our neutron. Okay. Okay, so fusion over fission. Fusion gives us a shitload more energy, right, compared to fission. So splitting it up, right, it gives us less energy. So we get more energy by fusing it together. There's no radioactive waste because we get helium, right? We use helium. We can put in our balloons, right? So just from our car engine, we can sit there and make helium and have our balloons floating at the same time, right? Which we're on a shortage of helium right Yes, we are. Have you guys noticed that? If you guys thought that, yeah,
Yeah, you said it was last few years, right?
yeah, it's actually for the last 2 3 years. Yeah. So disadvantages. This is the problem, right? This is part of the reason that we're having trouble, and also because there hasn't been enough money invested in it. It's extremely high temperatures that be required, so your engines are going to be running like super. And right now, there are no substances known that can hold the reactants that are required at these temperatures. Right? So you burn through the metals pretty fast. So you metals. Okay.
So why is he doing that?
Part of it is, well, it's due to COVID, and helium is actually it's isolated from the air.